You guys are probably here. Hopefully you guys are here to do some math, specifically math contests. Yeah, it'd be great if you could quiet down. Yeah, this is the math contest preparation course. We're going to be weekly on Thursdays, just this time. Same place, unless it seems, yeah, this is a good place hopefully for all of you guys. Thursdays until December, whenever that is. Yeah, there's going to be a lot of people who end up teaching this math class. For today, me. My name is Oliver Chang. I'm a grade 12 from Old Skona. These guys are all my classmates from Old Skona as well. You'll meet them eventually, but the second guy's Andrew, that guy's Alex, that guy's Jack, she's Alice, and he's Alex Kai. So, there's two Alexes. So, yeah, hopefully you look forward to them teaching because they'll probably teach pretty good as well. Alright, so I guess this is mine. Okay, that's kind of embarrassing. Alright, so let's start with, I guess I kind of want to hype up math a little bit, right? Because, I don't know, I do a lot of math. Math is like the only thing that I find enjoyable in my spare time in addition to volleyball. And I think for the most part, math is definitely something that is worth pursuing. I mean, for the first, in a sense it seems kind of pointless when you're just solving, I don't know, if you guys do math contest problems, you'll probably see, you probably do math contest problems and they set up some really weird scenario that seems completely pointless, and then you solve that scenario and kind of think, okay, well, great, what was the point, right? I mean, that's kind of the problem with mathematics in general. That's I guess that's the bane of mathematicians, right? That's what everybody kind of sees math as, kind of a little bit pointless, a bit you're just doing it for the sake of the problem, but not really for the sake of anything useful. Now, to a certain extent, I think that's actually true. Now, why would I admit that, say? I mean, I guess it's it's important to kind of notice that maybe we have the wrong idea of what math is supposed to be. I think a lot of the time you hear math as application, right? It's got so many uses, that's why you should learn it, because with a solid foundation in math, you can go anywhere. And that's true. Math provides provides you with a logical and problem-solving brain that would give you an ability to basically pursue any field. Even in the humanities, that solid foundation of mathematics, that problem-solving ability and those logical abilities are very helpful in reading and writing, right? And I know that because I have gotten moderately better at reading and writing after getting better at math. And you probably will find that too. But I don't think that's really the essence of math. I mean, sure, it's useful, right? I mean, almost every subject is useful, or else it would have been burned to the floor by now. So what is the actual essence of math? Why would a mathematician do math? Why would they get paid to do math, right? Why do we pay there's probably 20 or so professors that our taxes go into to pay them to solve problems every day. Why would we ever do that? Why would we ever pay them, right? For a certain extent, it's for their pleasure, I think. Because, I mean, when you do math, do you not find it a little bit fun when you solve a question? I mean, it's a bit hard to say in particular, but I like to think of solving math problems as a bit of an art. You never do art because you want to, you want to apply your music theory into another subject. You do art for the sake of art. You listen to music because it's beautiful and because it's nice to listen to. I think math is pretty similar. I mean, to a certain extent, you have those applications, just like music has a lot of ways that we can help other people. Like you don't only do it for pleasure, you can also do it for productivity and such like that. And art can be used for a variety of different reasons. But like at the core, math is for pleasure, I think. Math is for the sake of solving that problem, for getting that insight into whatever field you're doing. Right now we're just solving like disjoint problems in like random math contests everywhere. But as you get more into mathematics, you'll start really zeroing in on a certain subject in math. And I think that's when you really find that insight. Like for me personally, this summer, I went to Ross. I went to a summer camp over in China, and I just did 5 weeks of math every day, and it was probably one of the best 5 weeks of my life. And now, like, maybe that seems like kind of torturous to some of you, but the reason why I enjoyed it so much was that I was creating my own system of mathematics. At Ross, we built mathematics from something called axioms. Now, like, what is mathematics actually? Like, I would say mathematics is you trying to find the truth value, or like whether or not a statement is true in a certain system that you're constructing. Like, I think the easiest example is something like 1 + 1 = 2. Is that true in the integers? Yeah. Hopefully, right? And like, now maybe it isn't true in some other weird systems of mathematics, right? In some other weird number systems. Like, there's a lot of weird number systems out there that I don't even understand, like polynomial rings or whatever. Like, there's really weird things out there. So is this true in general for all numbers? Like, if I add an emoji and I add another emoji, do I get like 2 emojis? Probably, hopefully, right? But at the same time, maybe that emoji number system is a bit different. And like, I think, okay, so that was kind of getting off track. But like doing math and like starting from those foundations, starting from these things called axioms, these things that we assume to be true regardless of all else, is one of the like funnest parts of math. That's not a word. But what you get is like, you get a feeling of, how do you say this? You get a feeling of pleasure, but you also get a feeling of satisfaction because you created something from the ground up by yourself, and you were the one who explored that system of mathematics on your own to create those insights, to like show rigorously that 1 + 1 = 2. I guess that's the first bit of it. Okay, so I guess we can start doing some actual math now. What is this? Mr. Santos ordered 8 pieces. Alright, so I guess this is a math contest prep. So like do some math, hopefully. Yeah, what is the best estimate of how many pizzas? Oh, okay, let me read this out for you in case you guys can't see it. Mr. Santos ordered 8 large pizzas for a class party, okay? After the party, only 5/6 of the sausage pizza and 1/3, so like a mixed fraction, I'll write it out. 1/3. Right? Okay. So like a mixed fraction, not like 13/4. Of a pepperoni pizza remained. So like, which is the best estimate of how many pizzas? Wait, can everyone see? Like, yeah. Like if you can't see, like just kind of like. Okay. All right. So all of you guys can see. So I mean, like, I guess how do we solve this problem? So we're gonna start slow. We're gonna start with solving these questions. Yeah, don't worry.
How do we solve the question? 5, 6, and 1/3. This is go.
Okay, so
Excuse me?
yeah. Oh, you can see.
not an S.
No, I don't listen to Alex with.
Yeah, that's true.
And he wrote.
I don't want to listen to Alice.
I want Alex to wait. No, it's because I write the email.
Well, you actually solved it. I'm surprised.
Oh, so messed up. 5 out of
How did you not get this? This is pretty easy.
It's called subtraction. Or you can just subtract. Me too. I
swear I see that. I know, but what's the
Okay. I guess I'll go over the solution. Hopefully you guys have an answer in your mind. I don't know if you wrote it out. And I guess like the first thing we should do is you should understand the question, right? So what's the idea? We have 8 pizzas. I'll draw 8 pizzas. Each of these circles is a pizza. Is that so? Alright, so we got 8 pizzas. Now, when it says after the party, 5/6 of a sausage pizza remain. So you can think about it like, so we have 5/6 of a sausage pizza. So give or take, this is about 5/6 of a sausage pizza. So I know this much. We have at least this many pizzas remaining, right? So now we also have another piece of information. We have 1/3 of a pepperoni pizza remaining. Okay, so 1. I'll just write this as sausage. And this is pepperoni. And then 1/3. Okay, so you can think about this as how many pizzas. Hey guys, could we quiet down? Alright, so you can think about this as how many pizzas remain because we don't have any other information in the question, right? So, like how many pizzas are eaten, right? So I would have solved this using subtraction, right? First, how many pizzas are eaten? Well, it's the total number of pizzas minus the remaining number of pizzas. Does that make sense? Like, what's the formula here? It's like remaining pizzas plus eaten pizzas. Okay, so this is like the main idea, right? So, what's the total number of pizzas? 8. You have 8 total pizzas. So 8 plus, or 8 is equal to the remaining pizzas. Now how many pizzas are remaining?
Yes, I agree with that.
And then plus the eaten pizzas. And the eaten pizzas is our variable. So I'll just call this like S. Because we want to solve for S. So what is the number here? Can anyone tell me?
31 over 12.
Sure. 31 over 12. Is that right? Wait, is that right? Yes. So this is 31 over 12. Now we can subtract 31 over 12 from both sides, right? So then what we end up with is like x is equal to 5 7 eighths or something like that. 5 7 twelfths.
Five,
that
five
makes
twelves.
sense. Is it 5 something?
5 twelves.
So it's 5 5 up.
5 twelves. Yeah.
Alright, thanks guys. Fair, right? Everyone understands so far? Is there any problems? Yeah? If there's any problem, please give like a subtle thumbs down. Alright, sweet. So now, but like we have to be careful, right? Because the question says, what is the best estimate? And of how many pizzas? And when it says pizzas, we refer to total pizzas. So, is this number, is 5 5 twelfths closer to 5 or is 5 5 twelfths closer to 6?
5.
It's closer to 5. So our answer is going to be 5. Okay. That's good, right? Is everyone fine with that? Okay, so the diagram was kind of drawn bad, but no, maybe on that. Basically, don't look at the square, just look at the octagon. Yeah, so try this one.
later, later.
He needs gravity. Yeah. Wait, I allow it just like in the future, maybe some of the other counselors that they may not be a thing. Yeah.
No, I paper. I really don't take them.
No, I'm not there.
Wait, isn't this the
I don't know. Can you put in multiplication in your head?
I usually try to do it all in my head and then I forget.
Alright. That's fine, that's fine. I'm just saying, like, if you need paper, I have paper.
Wait, no, how do you get the answer? How do you get the answer? And how do you get the
He just tries to be stupid. I have to remember what the data
I get nothing. Are you sure I can't do this?
Because he didn't do it in grade 7.
Okay.
That's close? It was, he said that was close. Oh my god. How hard is it? What the hell? Eric, where's the Lord? The only probability was, the only probability that what are the chances of getting theoretically,
Yeah, 1 out of 6. I'll go over
3
the
over
answer.
8. 1 out of 8.
I'll go over the answer. Okay.
Okay. Let's see the percentage to cover all. Let's bet the percentage to cover all. The only reason I passed the grade is because I'm pretty sure it's making us all govern. I know it's making us all govern.
Alright, so hopefully you guys all had like a bit of a chance to try the problem. I guess what we should first do is make sure we understand what the problem is asking. The diagram wasn't the best, that's my apologies. But think about it as like we have an octagon, right?
Very good. Okay, I take that. Okay, I take that.
Alright, so we have your octagon. Now, what we want to do is we want to make a triangle, right? But the triangle's edges, or the triangle's vertices can only be on these vertices. Let me write it down. So the triangle's vertices can only be on the octagon's vertices. So for example, one possible triangle I can make is this. Yeah, this is one possible triangle. And what the question is asking is, right, is that how many, like what is the probability given any such triangle that's formed in this manner that the triangle contains an edge that is exactly one of the edges of the octagon. So for example, one such triangle could look like this, right? Because this edge is on the edge of the octagon. Another example would be this triangle, because there are two edges that are on the octagon. All right. Valid.
Yeah, there's going to be also 2. Are there easier questions? Yeah, we don't care.
Alright, so these are like the two types of triangles that can like kind of like exist. Right? There's one other case. This is with one side. Are you still octagon? Is it an O? Is there anything close? It's octagon.
No, it's octagon.
It's an octagon.
It's octagon. It's like this high school and it's all that. It's just wondering, you take out A. I'm pretty sure it doesn't take out. You take art in LA.
You gotta reverse it side by side.
No, that's one. I feel like it's what I say. See, you
Alright, so like from this, what do we want? We listen up. Guys, be quiet. Alright, so like what do we want? We want to find the sum of these two divided by all possible triangles. Yeah? That makes sense? So, I mean, one thing we could do, like there's quite a few methods to tackle this. The first thing I'm going to do is I'm just going to count the number of possibilities in these two cases. Okay? I think this isn't too bad. So if I had two sides on the octagon, where can the vertices be? That's the question. I think it's pretty clear that the vertices have to be adjacent to each other. And when I say adjacent, I mean like it just have to be consecutive vertices. Does that make sense? Yeah? Like if I had to have two sides, right? Like let's just say, for example, maybe I had two other sides on the octagon. If I had an octagon, I had two other sides that were, and I chose like these two sides, and they weren't adjacent sides. How the heck do I make a triangle out of like these four vertices? That's not really possible. So we can be pretty confident that the three vertices on the triangle have to be adjacent vertices. Okay, so now how many possible triangles are there? Well, there's like this one, right? Then there's this one, and there's that one, and there's that one. And like, it's just the three adjacent vertices, right? And like, we can start on any of the vertices of this octagon, so there are 8 total possibilities here. Does everybody see how I got that? If you don't, please like, give me a thumbs down, or like, get angry. Right. Okay, I guess I can try to explain it a bit better. So if I have an octagon, I can just draw out the 8 possibilities because I guess that's not too large. This is one possibility. This is another possibility. This is another possibility. And this is another. Forget it. Well, I mean, it's kind of hard to see, but we can count 8 here, right? And are we absolutely confident that there are no other possible triangles? Yeah, because like of what we just, of our thought experiment, if there was another triangle, then the two sides couldn't be adjacent, and if the two sides couldn't be adjacent, then what would have to happen is there would have to be a quadrilateral, which is definitely not a triangle. So we have 8. Okay. So the next question is, what if we have one side on the octagon? Okay. Well, we can kind of, now we need, like, to solve this part, if I want to be a bit lazy, I have to invoke something called counting round. So, oh yeah, does anyone have any questions? What? What do you mean by call the triangle adjacent? Right now I'm saying like the points are adjacent.
Oh. Then why do
You
you
see on the
use
diagram?
Yeah. Cause like I know adjacent is a triangle.
Oh, okay, so maybe I should have defined that. Oh yeah, if you can't see, like there are other spots that move, so just make sure you can see the board. So when I say adjacent, maybe like an equivalent definition would be like neighboring points, adjacent points.
What's the adjective? An adjective? Adjective. I don't know.
Does anyone have any other questions? Alright, so now we have 2 sides on the octagon. What we want is 1 side on the octagon. So, like how would we actually approach this? There's certainly way more triangles in this certain case. So we wanted, like, obviously, I don't want to count them all. I'm not going to do this thing. It's going to take a bit too long. So the first, like, what is the information that I gather from my case? Because the nice thing about breaking this into cases is that we've simplified the problem, right? We've restricted the possibilities that these triangles could be. So if there's one side on the octagon, then maybe the first thing we do is we find the number of ways we can pick one side on an octagon. So how many ways can I pick one side on an 8-sided octagon?
Octagons are always
1 out of 8.
8, right? There are 8 possibilities to pick one side. That's not too bad. So there's 8 possibilities to pick one side. Okay, so now, like, just for example, maybe I pick this side. All right? Now, I need to make it into a triangle, right? I've already gone 2 vertices. Now I just need 1 more. That's not too bad, right? But can I pick, like, how many vertices are valid vertices that I can choose? Well, let's think about it. Oh, okay, sure. Like, let's see. Sure. Yeah.
5 valid vertices.
Not quite. Sure, the person at the back. Yeah, there's 4. Now, why is there 4? Well, let's look at each one of the vertices and see whether or not we can choose it, right? So, like, okay. So immediately, we obviously, like, we can't choose this vertice, right? These 2 vertexes are already chosen as parts of our triangle. We can't repeat. That's not a non-degenerate triangle. So what about this? What about this vertex? If I choose this vertex, what happens?
It becomes a 2-side.
Exactly, it becomes a 2-sided. It's no longer that case that we're looking for. It's something we've already counted. And we don't want to double count, right? We've already counted the 8, so we don't want it to be either here or here. So maybe I'll put like that. Okay. Alright, so we don't want it on these 4 places, so the only remaining vertices are these 4, and we can be pretty confident that each of them work, right? Each of them will produce a unique triangle that has exactly 1 side on the octagon. Yeah? Any questions with that? Okay. So then how many possibilities are there? So there are 4 points, 4 possibilities for the 3rd vertex. So this is where we have to invoke something called a counting argument. Maybe you haven't seen this, but basically what I claim is that this is actually equal to just 8 times 4. The number of possible ways for there to have a triangle such that only 1 side is on the octagon is 8 times 4. Okay? So now we have 8 times 4, and then we have 8 from the original one. And now we're trying to find a probability, right? So now we want to find the denominator. And this denominator is essentially going to be all triangles, or a number of all triangles. Okay. So there's one last step. You have to find the number of all triangles. Wait, does anyone have any questions so far? Make sure we didn't lose anybody. Okay, great. So how do we find the number of all triangles? All right. So this invokes another counting argument. What we want to do is when we take our octagon, the idea is how many ways can I choose the first vertex? The first vertex can be any one of these 8 vertices on the octagon, right? That's fair. Okay, so I'm just going to say, for example, maybe it's this one. All right? Maybe I chose that vertex. Okay, so now how many vertices are remaining? Like for the second vertex, this is the first vertex. For the second vertex, it certainly can't be on this same first vertex. So it's one of these 7 vertices. Okay? That's fair? So I'm just going to pick this one, but it could be any one of these 7. So I'll write, there are 8 possibilities here. And there are 7 possibilities here. And now for that last third vertex, it can't be the second vertex, and it can't be this first vertex. So it can be one of these 6 vertices. I'm just going to pick a random one, but it could be any of the remaining 6, right? So this is the third vertex. Okay, so now we have to use, how do we find the total number of possible triangles? So the idea is it's just 8 times 7 times 6. Sorry if you guys can't see on that side, but all I wrote is 8 times 7 times 6. Why is that true? This uses something called the fundamental theorem of counting, which is basically that you can multiply things to get the number of possibilities. But hopefully it kind of intuitively makes sense. There's 8 possibilities for the first one. So okay, we have 8. We've created 8 possibilities. So then we have 7 possibilities for the second vertex. So out of each of those possibilities for the first vertex, there are another 7 for the second, right? So 8 times 7. That's how we get 8 times 7. Now, we've already picked the first 2 vertices. Now we have to pick the third one, and there are 6 vertices there. Try to figure this out in your head. I think you'll notice if you actually try to do this with maybe smaller case examples, like if you try this with, if you try to put triangles into a square or something, you'll realize that the number of ways I can put a triangle in a square where the triangle has the same vertices as a square is just going to be 4 times 3 times 2. Because there are 4 places for the first vertex, 3 places for the second vertex, and 2 places for the last. So, yeah, try to think that through. The explanation and the actual proof for it takes a bit of time, so I'm not going to go over it. But this would all be over 8 times 7 times 6. But one thing we have to notice, one thing that's very important, is that when we took this 8 times 7 times 6, we didn't distinguish between which vertex, right? Like, we kind of assumed that this first vertex, this second vertex, and this third vertex were distinguishable. But they aren't really, right? Like, if I were to draw my triangle, if I drew a triangle that was like this, and then I drew a triangle that, how did I draw the triangle? I took 1 to 3 to 2. But then if I took another triangle and I drew it like this, that's the exact same, this is the exact same triangle, right? But I drew it a different way. And maybe you notice that, okay, we've overcounted. We counted this same triangle exactly 6 times. And you should see that you understand why it's 6. Because there are essentially 6 ways that I could have chosen these 3 vertices. So we divided by 3 times 2, which is equal to 6. Okay, just do the algebra. You get 5 over 7.
5 over 7? Oh, let's go! That paper I got it right. Well, you get 3. Okay.
Alright, so
I got it right back down.
5 over 7? Yes! Oh, 5 over 7. Daniel, I got it. No, say this is that big round. Wait, I have a question, Daniel.
yeah. Does anyone have any questions? Yeah, just raise your hand. If you want me to re-explain something, that's fine too. Yeah.
How do you get 876? Isn't 8 by 7 by 6?
Yeah, this is 8 times 7 times 6.
Isn't that 336? Or am I just blind?
Wait, no, like 8 times 7 times 6.
So he wrote dots, like
Yeah,
multiplication.
I know that.
And there's no
Yeah.
bracket.
So like,
Yeah, that is very good.
like I never evaluated 8 times 7 times 6 because I can't do that in my head.
It's yeah, 336.
Take a bite. Take a bite.
Is anyone like very displeased with how I solved this problem? Is anyone very angry at the fact that I solved this problem in a way that maybe is not the same way that you solved the problem? Sorry? Yeah.
Choose this side, right? Two questions, you only count 5 of them, but you don't count the one that's like,
Directly against. Yeah.
this is 2 times 5 divided by what you did over there, that's
Yeah.
50.
That's another way.
All he did is
Are you the heck for writing random stuff? Guys, we have to put this on the snake. I'm betting my rocket. I got it. I didn't bet it yet. I didn't know. Oh wait, man. Wait, not yet. Give it to me. No. Okay, I'll give one to every bet.
Sorry, it's something invisible. Maybe you should try saying something.
Oh, get these are like our wait. I'm ready to do about it. What is there?
Oh, ours will be 8.
Are we done?
What is the greatest possible?
Alright, so we're gonna do one more question. If you guys have to go, just feel free. That's true.
I don't care. Why did I have to be 29? Oh, for Terry Fox. Yes, he stole it. Wait, question 3.
I'm gonna go now.
We just took questions.
Don't eat it. They're like so. Take 2 or 1 or 2. What time is it? What time is it? No, You're just, no, get perspective. would be somewhat like 21. I know. There's someone from 1 to. I know that you can't. But you're up.
It has to be smaller than 2.
Yeah, and if you're not be down, it has to be above here. But above here, it's less than 2019. Wait, positive number is not decimal factor. Base 7.
Oh, absolutely not.
Whatever time is right now.
It's 8:02. Wait, are you gonna give us the answer to this?
So 100
Clips hanger.
Oh,
Oh yeah, I'm not coming.
Stop him down. I'm not gonna believe it. Wait, what is the great constant when the data is subject? Wait, representation of all the picture. So you guys switch classes?
Yeah. You'll find some very capable people teaching you.
Hey guys, you're
You'll
lucky
also
you're
get
both
very
kids now.
different kinds of people teaching you.
Hello, one. It's basically everything very cheap.
Okay, this is the only thing. I'll take care of that. This is the only thing that I got.
It's the answer to it only goes up to
You
7.
wait for me air.
Alright, what's base 7? What's base 7?
What? Wait, guys, tell me. Guys, tell me. How is that? Guys, tell me. How does the beer? 7, 14. Oh, so every 3 days that's like the anytime to answer. Like what?
Wait.
Well, he's been missing a hanger. Wait. I know. But you'll 799.
6 plus something.
Isn't that a basic grade? 799. Isn't that a grade? I might actually wait, do you want the 799 down? Please. Yeah, I know. It has to be smaller than 2018. It has to be 2019. Oh, you know, I already wrote it. It's not a thing. I wouldn't know.
Yeah, I'll let you.
Wait. No, I got told.
Okay, this doesn't work for sure. That's not going to be fixed.
Although base 7 is like base 8 is 76, so
I'm going home.
it only goes up to 7.
Go die in a hole.
Like it's up to 100 digit, it's 49 digit.
Wait, can you reach your
It's up to like 1,000 digit.
I took my phone. I wrote on my phone.